Welcome back. So this is section 2.1, and it's idea of a limit. And that's the first actual section topic of calculus, and because before we were just reviewing pre-calculus. So in general, we have two branches of calculus, right? So first branch that we will start with those particular topics. It's called differential calculus. And so that, right, we'll be calculating derivatives. So we have two types of notation for derivatives. We have more types, but we'll be using just these two, I think, if I remember correctly. So dy dx would be a symbol of a derivative, and also f prime of x. Right? So these are calculating derivatives of a function with respect to x. Okay, so that's the first branch, and then after we're done with that, we'll look at integral calculus. And we'll be calculating antiderivatives or simply integrals. Okay, so symbol for integral is this squiggly line, then there's a function, and then this dx basically tell us what variable we're calculating that integral with respect to. Yeah, so in general, calculus is just a math or mathematics of change. So when you're studying pre-calculus, algebra, or even physics, right? Before you've been introduced to calculus, we're basically dealing with things that are constant or average. Right? So let's say you're trying to go from Honolulu. Let me give you an example. Honolulu to Haleiwa. The distance is about 50 miles. Right? So 50 miles, and let's say, and it's gonna take you maybe about 1.5 hours. So traffic is heavy, 1.5 hours. And if you're trying to figure out speed and velocity, the only thing you can do is figure out average velocity. Right, so you would take, let me get the second page. You would take distance, and to calculate velocity, and its distance over time, right? Miles per hour. So you would take distance and divide it by time. So distance divided by time. So we had, what did we have? 50 miles divided by 1.5 hours. Right, so we divided and we get 33.3. And this is in miles per hour. Right, so we would get some average speed at which you would cover the distance. The problem is when you look at the speedometer, right, in your car, that speedometer rarely shows that speed, or maybe never, right? It's usually faster, a little bit slower, or sometimes you're just stopped at the traffic light. Anyway, so that's what calculus will help us, right? Calculus will help us figure out what the instantaneous speed, what speed is at a certain particular moment. Okay, so calculus tells us instantaneous speed. Okay. Yeah, so when when you look at the right when you're looking at this particular problem or example from the algebra point of view, right? What is happening is this, right? So let's say this is and coordinate system. On the x-axis we have time, on the y-axis we have distance, right? So distance. And when you look at and your journey, your trip from Honolulu to Haleiwa, it would look something like this. It would just be straight line, right? And then to figure out what the velocity is, right? You would figure out, or that average velocity. You would simply calculate the. Right, so this is your Honolulu, and this is Honolulu. This is Haleiwa, and you would just take. Right, so then we can put this 1.5 hours over here. 0.5 hours, and then distance of 50 miles. That would be here. Right, and to figure out that speed, right, you could do what we just did, right? Speed would be the slope of that line, right? So that point is 0, 0, right? And this point is 1.5, 50. Okay, so to figure out slope, you would take 50 minus 0. That would be, right, it was y2 minus y1. And then in the denominator, you would take 1 minus 0. Right, so x2 minus x1. So that's how you would get that velocity or the slope of that line. Okay, so that was, what was that? This is 1.5, by the way, not 1. Okay, so we got that 50 over 1.5, right? And we have that 33.3 miles. Well, unfortunately, right, this is not what's happening in reality. Right? In reality, what's happening is this. So let me make another graph. I mean, this will be some kind of approximation, right, of reality, or some kind of example of what might be happening. Okay, so so similarly, this will be this is Honolulu, right, and this is Haleiwa. Okay, I may make a couple attempts with this graph. Anyway, so let's say, right, so you're starting and you're speeding up a little bit, and then, right, you're going at certain speed, and then you're slowing down, you're stuck, let's say, at the traffic light, and then you start again, and then you're maybe going a little bit slower, a little bit faster, okay, and then you slow down, arrive at Haleiwa. Okay, so if we wanted to calculate, right, so this is still 1.5, by the way, right, so 1.5 hours, and this is still 50 miles. So let's say you're trying to calculate the instantaneous speed at this particular moment. So this was, I don't know, maybe 10 minutes or 12 minutes after you started. Right, so what you would have to do, and this point would be here. Right, so you would have to take, this will be here. I don't know, we could figure out what that is. Something, I don't know, 6 miles. So you would have to draw a line, right, that touches that curve at that particular point, and this is called the tangent line, and you would have to figure out the slope, right, of that line. Unfortunately, right, we don't have 2 points, we only have 1 point, right? And that's kind of the first idea of calculus, and the first idea is going to be the limit. Anyway, right, so that's a big question mark. What's going to happen right there? So let me start with an example with actually simpler curve, right? Because this is quite complicated curve. Anyway, so let's do example 1. And so what do we need to do? Find an equation of a line tangent to a graph of, let's take just a simple curve, x squared, so it's that basic parent parabola, and at a certain point, at point P, and the coordinates are 2, 4. Right, so you see that this point is on the graph, right? It's because if you take 2 and plug it into the function, into the equation, you get 4. All right, so let me draw the situation first, and then we'll talk about it. So yeah, we don't really care about the left branch of the parabola. We don't care what's happening on the negative side. So I'm just going to graph it this way. Right, so here's my parabola. I think I'm just going to keep it like this. This is called the same color. So white. Okay. So this is y equals x squared. And what are we doing? We're doing a line tangent to that curve at 2, 4. So that's, we don't have to be particularly exact. So let's say that 2, 4 is right there. So this is point P, 2, 4. Okay, so at this point, we're just unable to calculate that, right, the slope at that point. But what we can do, anyway, let me draw that line actually, that tangent line. So tangent line, and is a line that touches a graph at a certain point. And okay, so we have the tangent line. So what do we need to calculate? The slope of that line. Okay, so we need to figure out. So for now we can't do it, right? But what we can do, we could pick another point. Let's take maybe point. What can we do? Maybe this one. I mean, and this will be Q, point Q. And for now, let's have specific particular coordinates. Right, so it'll be 3, 9. Right, so we cannot calculate the slope at a particular point for tangent line, but we can definitely calculate the slope for a secant line. Secant line intersects 2 points on a curve. Right, so you see the one that the line that I'm drawing is actually a little bit steeper. Right, so I have that point Q, 3, 9, and I have a point P, 2, 4. And calculating slope, right, is trivial. Right, you just take the formula for slope. So that was y2 minus y1 divided by x2 minus x1. Okay, so what do we have? Let's assume this is, right? This is y2, x2. This will be y1, x1. And I'm not drawing those. I'm not writing those letters, just to keep everything clear. Anyway, yeah. So let's put the numbers in. Right. So y2 was 9, y1 was 4. So it's going to be 9 minus 4, and the bottom is 3 minus 2. Okay. So what we get is 5 divided by 1. That's 5. Okay, so yeah, so we got the slope of the green line, so m equals 5, but that's not really what we want. That's not what we need, right? We need the slope of the green line, the line that touches, sorry, the slope of the red line that touches the graph, the curve, right? It's not a secant line, it's a tangent line. Anyway, so what we'll do, we'll take that point Q and we'll make it, a little more abstract. So instead of picking particular coordinates, I'm just going to write that Q as x and y. Sorry, x and y. Where's my green? All right, x is just x, and y is x squared. Right, so you guys see it. Y is x squared. So I'm going to replace that y with x squared. So I'm going to write Q. Right, so my point Q will have coordinates x squared. Yeah, it's a bit messy, but that x, and I hope you see that square right there. So now, if I want to write that the formula for slope, right? Instead of taking those particular numbers, right? I'm going to take x squared and x. Okay, so slope, so some kind of general formula for slope is going to be course. Right, so general formulas for slope. So m, and it's going to be x squared. Right, so that x squared comes from this. Okay. Now, so that's my point Q. Point P, right, is right here. And I'll have, right, coordinates are 2, 4, right? I'm not going to make these two coordinates variables, right? Because, well, that point is kind of, right, this point is stationary, right? And this point, right, is in a sense more abstract. Anyway, yeah, so let me finish that formula. So it's going to be x squared minus 4. And then the bottom, is x minus 2. Okay, so we have this general formula for slope, and what we'll do next, we'll take this point Q, right, and we'll move it closer and closer to point P. Right, so that line, the green line, is going to be getting closer and closer, right? The slope of the green line, and this line. If I'm moving that point Q, right, closer and closer to point P, and you guys see that if I have this point Q right here, right, then the secant line between those that connects these 2 points, that intersects these 2 points, will be very, very close to the actual red line, right, to the slope or to the line that I actually need. Okay, so what I can do, I can maybe make a table with those x coordinates, right, getting closer and closer to 2, right, and then I have y coordinates, right, getting closer and closer to 4, and calculating, right, those slopes one at a time. All right, so let's do it. So this will be called, right, numerical approach. Okay, so let me open the new page. Let me write that formula for slope, right, our new formula. So that was m equals x squared minus 4 x minus 2. Okay, so now here's the table. Right, so we have our x's, and we have slope, right? So if x was 3, right, slope was 5. All right, so next thing we'll do, we'll make that, right, that x closer to 2. So let's pick 2.5. All right, so I have m equals, right, so we have 2.5 squared. And I'm plugging the 2.5 into the, right, so I'm taking this x and I'm plugging into formula for slope. Okay, so I have 2.5 squared minus 4, and it's divided by 2.5 minus 2. Okay, so we calculate it, and we get, let me see. Okay, so we get 4.5. Okay, so that's the next slope, right, between those 2 points on the curve of that secant line. So the slope is 4.5. All right, so let's do 2.1. Okay, so again, right, so we calculate that slope. So we have 2.1 squared, and then minus 4, and the bottom is 2.1 minus 2. Okay, again, right, we'll put it in the calculator, and we get slope 4.1. So 4.1. Right, and we could continue with this. Let me just give you a couple more numbers here. So 2, so 2.00001. Right, so I'm very close to that x equals 2. Right, and then the slope will be 4.1. I have 3 zeros, 1, 2, 3, and 1. And then if I plug in, right, I don't need to pick x's that are getting closer to that 2 from the right, right? I can also pick something that's below 2. So 1.999999. So I'll have 3.9999. All right. So you guys see what's happening, right? So the closer I get to the number 2, right, with my x's, the closer I get, the closer the slope gets to m equals 4. So we're going to conclude that the slope of that line is 4. Okay. Another thing we can do, right, when we look at that formula for slope, right, so let's look at it. So it's x squared minus 4 divided by x minus 2. And yeah, we can factor the top, right? So it's x plus 2, x minus 2. And we get the denominator x minus 2. Now we can, right, cancel this. And we get x plus 2. Okay. Yeah, so at this point, I guess we can plug in that, right? Plug in that x equals 2, and we get 4. Okay. Yeah, so we did a little bit of algebra here. We could also do calculus, right? We can take a limit. So let's do that. I know you guys don't know what that means, but I'll explain in a moment. Take a limit. Okay, so we'll take a limit with x approaching 2. All right, so let me actually calculate that limit. So I have x plus 2. Right, so that's my final, right? I'm taking this, right? I could take this, right? I could take this this equation, this formula, but yeah, then I'm simplifying it, right? So essentially it's the same as this one. Well, not really the same, but anyway, for our purposes it's the same. So now we can plug in that 2 into this, right? X plus 2, and we get 4. Okay, so that's the slope, that's the limit. But yeah, let's finish our problem, because we were supposed to calculate find the equation of the line, right? So the only thing we did, right, was to find the slope. Well, that's the most difficult part, right? Anyway, so the last thing, we'll take this point slope form. So that went something like this: y minus y1 equals mx minus x1. Okay, so we have y for in our point, right? The point was 2, 4, right? 2, 4. Y1 is 4. Slope was also 4. Yeah, too many 4s. And then this was x minus 2. Okay, so yeah, if we clean it up a little bit, right, we get y equals 4x minus 4. Okay, so that's the equation of the line, right? Tangent to that point 2, 4. Okay, so what is the limit? Let me give you a definition. Yeah, if f of x, the value of a function, becomes arbitrarily close to some number L, erase that, number as x approaches c, so number c from either side, the limit of that function of f of x as x approaches c is L. Okay. Yeah, so that's the definition of a limit. So let me write the notation for it. So x approaches c of f of x equals L. Okay. So basically we'll be calculating value of a function as x's approach a certain number. Okay, before I'll give you examples, let me explain quickly the difference between x squared, right, our original formula for slope, minus 4, over x minus 2, difference between this and x plus 2. Okay, so what we did, right, we factored the top, and then we simplify this whole thing to x plus 2. So basically, this would be, this is a rational function, right? So x squared minus 4 over x minus 2. And the graph of it is actually, let me show you the graph. Okay, so we have, right, so that slope was, or that the formula for slope was that x, let me write it, right? So the formula for slope was x squared, or that expression, right? Right now I'm just kind of explaining the algebra side of it, right? Minus 2. So that's simplified to x plus 2. Right? So the difference between just x plus 2 and, right, if I wanted to graph x plus 2, I would just go, right, so it's going to be a straight line. Right, so something like this, lifted up or moved to the left by 2. Right, so that's just y equals x plus 2. And now if I want to graph this x squared, right, if I want to graph this, it's basically the same graph. The only difference is that I will have there will be a hole. I'm not sure if I can like draw that hole. I mean, right, so if this is 2 over here, and there will be a hole at that 2. I don't think I can, yeah, because if I try to erase, right, make a, you guys probably know how to do it, right? Anyway, right, so let me draw that hole, and now, right, we have the graph. We have that straight line, right? The straight line doesn't really change. Right, so now the graph that I have here is not really x plus 2, it's that x squared. Right, so let me, so this is a graph of that. If I don't have hole, right, then it would be this. Okay, let me make another comment here. So when we take a limit, let's write it. So when taking limits, it doesn't matter what happens at that number c. Doesn't matter, should be 2 t's, what happens at c. Okay, so it doesn't matter what happens to c, what matters is what happens close to c. Yeah, so what matters is what happens close to c. Let's write it. Okay. Yeah, so you see, right, that if we took a limit, right, of this expression, right, and if we wanted to calculate that limit, so let me change to actually a pen. So limit with x approaching 2 of x squared minus 4 divided by x minus 2. And if we were trying to figure out what happens at 2, we would not be able to, right? Because if I plug in that 2 into my expression, right? If I especially, right, if we look at the denominator, I would get 0 in the denominator. So I would have 4, right? I would have 0 on the top as well, 0 over 0. Right, so it's an indeterminate form. And yeah, it basically doesn't really mean anything in this context. So in a sense, right, that's what it means, right? It doesn't matter what happens at 2, because at 2, right, the function is not even defined, right? I have a hole right there. There's no function there, right? So what happens is, what matters is what happens close to that 2, right? What value that expression takes when I get close to 2, and that value was 4. Okay. All right, so let me quickly go over and what we just did. So what we were trying to do is figure out, right, our task was to find the equation, or right, we could this could be this could be a graph of car velocity, right? So you see the car starts at, right, stationary and then speeds up, right, and the velocity of the car increases just the same as the slope, right? Because essentially that's what velocity would be, right? If I had t here and distance there, and velocity would be distance over time, that would be slope of that line. Anyway, so we're trying to figure out the equation of the red line, this one, right? And we start with slope, right? We started with, we picked a point, 3,9, that's on that graph. We drew the green secant line, and we figured out the slope of that particular line, and that slope was 5. Then we decided, well, instead of having the particular specific coordinates for that point Q, let's just pick some arbitrary abstract coordinates, right? So x, y, and then we replaced y with x squared, because that's the equation of our function, right? You can see it here. Right, and we came up with this formula for slope, right? Some general formula. If I pick different points closer and closer, if I pick different points Q closer and closer to point P, right? And the next thing we did, using that formula, we created a table with different x's getting closer and closer to that 2. And you see that I'm starting with 3, then I get 2.5, 2.1, and using the formula for slope, we calculated the slopes. And right, just looking at those numbers, we concluded that the slope of that line is going to be 4. Okay. And then basically we took a limit. We calculated the limit. And so we took this expression and we plugged it as a function that we take a limit of, right, with x approaching 2. Right, so basically this, right, could be here. This is just a simplified version of that. And yeah, so when we actually cancel that x minus 2, right, I don't have that 0 in the denominator anymore, because I don't have a denominator, right? I just have x plus 2. I plugged in 2 in for x, and I got 4, right? So we confirmed basically the same result, right? So this was a numerical approach. This is an analytical approach, right? Calculus approach, all right? And then we finished by calculating the actual equation, finding the actual equation of the line.